Hello, welcome back. Let's look at a few examples of how to apply the diagonalization theorem. And by the way, if you noticed in the previous video that this said eigenvalues right here, that was a mistake. My assistants will not be getting a Christmas bonus this year as punishment, but it has been fixed in this video. Anyways, let's look at example 3. Suppose that A is a 3 by 3 matrix with two eigenvalues, lambda 1 equals 4 and lambda 2 equals 5. Every eigenvector corresponding with lambda 1 is a multiple of the vector b1, which is 1, 2, 3. And every eigenvector corresponding with lambda 2 is a multiple of b2 with components 4, 5, 6. Is A diagonalizable? Well, let's see. So what the theorem says, the C we're talking about is 3 in our case, and A is diagonalizable if and only if A has 3 linearly independent eigenvectors. So can we find 3 linearly independent eigenvectors of A? Well, let's suppose x1, x2, and x3 are eigenvectors. Now, to be an eigenvector, you must be associated with an eigenvalue, and that eigenvalue must be either, in this case, 4 or 5, and there's only 2 of them. So it might be that x1 and x2 are associated with 4, and x3 corresponds with 5. And in that case, x1 and x2 must each be a multiple of b1. And if two of your eigenvectors are multiples of b1, that gives you a linearly dependent set because one of them can be written as a multiple of the other one. They're both on the same line through the origin. So that would mean you do not actually have 3 independent eigenvectors. And we don't know which 2 it is. Like maybe x1 and x3 correspond with 4 and x2 corresponds with 5. Who knows? Or it might be the other way around. Maybe 2 of them correspond with 5 and 1 corresponds with 4. So the same thing would also be true. They would just be multiples of b2, and having both of them be multiples of 4, 5, 6 would give you a linearly dependent set. So putting these two things together, it must be one or the other. Like either 2 of the eigenvectors correspond with 4 or 2 of them correspond with 5, but you can't have only one corresponding with 4 and one corresponding with 5 and then the other one corresponding with something else because A only has 2 eigenvalues. So whichever one of these eigenvalues corresponds with 2 of these eigenvectors, either way, you're going to have a linearly dependent list. So yeah, there is no list of 3 eigenvectors that is linearly independent, so A is not diagonalizable. Okay, let's look at example 4. Suppose A is 3 by 3 again, with 2 eigenvalues, lambda 1 equals 4 and lambda 2 equals 5. Every eigenvector corresponding with lambda 1 is a multiple of b1, the same thing, and the set of eigenvectors associated with lambda 2 is the span of b2 and b3, where b2 is 4, 5, 6, and b3 is 0, 3, 0. Now, in this case, b1, b2, and b3 are all eigenvectors, and we can actually see that they are linearly independent. To see that they're linearly independent, well, I don't know. I guess I can see that 1, 2, 3, and 4, 5, 6 are not multiples of each other, and 0, 3, 0 is probably not a linear combination of the other ones. Maybe we could row reduce it to check. I just pretended that I row reduced it in my head really quick. And yeah, that is a linearly independent list of eigenvectors. So according to the theorem, yes, A is diagonalizable. And specifically, A is equal to P times D times P inverse, with P equal to this B1, B2, B3 matrix, and D, the diagonal matrix, where the eigenvalues correspond with the eigenvectors in P in corresponding left to right order. So here we have B1 that corresponds with lambda 1. So this should have a 4 here in the first row, first column here. And then B2 and B3 are eigenvectors associated with lambda 2, which is 5. So we need to have the 5 in the second and third columns. Cool. Okay, let's keep going. Let's look at example 5 here. So let A be this matrix. It's triangular, but not diagonal. This is the matrix for a horizontal shear transformation. So if you do E1 is right here, A times E1 is not changed. You can check if you want that A times 1, 0 just gives you 1, 0. And A times E2, E2 being the vector 0, 1, is going to give you negative 2, 1, which is over here. Okay, so is A diagonalizable? To use the theorem, we want to know, does A have two linearly and independent eigenvectors? Well, let's see. Can you think of one eigenvector here? Maybe pause it and tell me if you can think of one eigenvector, because I will tell you in a moment. E1 is one eigenvector. Why? Because A E1 is equal to 1 times E1. So it's corresponding with an eigenvalue of 1. Okay, so we have one eigenvector. Now, to get a second eigenvector that is linearly independent from E1, well, we don't want anything that's on the x1 axis, because then the second vector would make a dependent list. So something that's not on the x1 axis. So I don't know, thing over here maybe, if that's your like x2 vector. Well, A times this x2, just following what happens with the grid lines here, is going to be over here, which is not a multiple of x2. If we try something else, I don't know, down here, if this is our thing we think is maybe a second eigenvector, well, that's actually going to end up way over here when you shear it. So anything that's not on the x1 axis is not an eigenvector, because it's going to get sheared away from the line through it and the origin. So no, A is not diagonalizable. Such a long word, you can't even write it on one line. All right, that sounds good for now. Let's take a little break and do some more examples in the next video. So I will see you then.